We're going to talk about variable frequency drives now and demonstrate with our MAC how they can affect the water flow and pressure and the system performance. We have a slightly different screen we want to take a look at that shows some different components to it. It's still basically the same as the initial screen, but it's got a few subtle differences. First, we have our total dynamic head in feet here on the left. On the bottom, we have our flow rate in gallons per minute. Where the two red lines intersect is our operating condition of the pump. Right now, currently at 138 gallons a minute with about 47 feet of head. Now, what we don't have on this screen is the bar graphs from the previous screen. But we still have all those same components being read. On the bottom here, we have the load profile, and we're going to insert numbers to determine what the load profile of this particular pumping system is. And then we're going to change the speed of this pump using the variable frequency drive. We also have what the total acre feet we're going to pump for the season is, so we can see what kind of energy savings and cost savings on our power bill we might expect with the use of the variable frequency drive in this particular scenario. So we're going to start out by looking at our pump curve here. We're going to choose a spot where we think we need to be at full speed. This is full speed, 1,780 RPMs currently. This is what the different curves would look like at different speeds, 1,600 RPMs, 1,400 RPMs, and 1,200 RPMs. But since we're full speed right now on this curve, we're going to stay on that. And we're going to use our valve to change the dynamics of the system. Okay, now I've set it at almost exactly 70 feet of total dynamic head because we've decided that's what we need to maintain on our pressure of our system at all times. I'm going to set that point at that particular 70 feet of head with about 121 gallons per minute of flow. Now, using our valve, we're going to change the output of this pump. Then we'll come back and compare using the variable frequency drive, how that affects the output of the pump. So right now, we are not using the VFD. We're going to say that on our first load profile point here, 122 gallons a minute with 70 feet ahead, the cost is $19.44 per acre foot. Now I'm going to use the valve to slow the flow down. I tried to get as close as I could to about 90 gallons per acre. These readings bounce around just a little bit, adjust it slightly. And we'll save that point. I'm going to set the point on the curve also. So now we have two different points of our load profile at full speed. Again, I'm going to turn the valve and shut the flow down a little bit more. Okay, we'll set this point. And this point is set at about 57, 58 gallons per minute. So now we know the different profiles our irrigation system needs to run efficiently. Perhaps we have different acreages or different size blocks, and so we need different flow rates. But instead of using a valve like we did in this first example here, we're going to go back and use the variable frequency drive to slow the RPMs on the pump motor down to create the same conditions. And we'll check to see what the cost per acre foot is when we compare that. I'm going to speed it or open the valve back up so we get back up to our full speed. Oh, tricky. Okay, now at full speed there is no savings, so with or without the VFD, our cost is about the same. Just the bouncing of the readings causes it to change slightly. But I'm going to set that point again. That's our set point. Now I'm going to hold 70 feet of head. And right here at the bottom of the screen, I'm clicking hold at the bottom of the button there, and 70. Now when I close the valve, it'll maintain that 70 feet of head and change the flow rate as I close it. I'm going to slowly close the valve. And you can hear the pump start to slow down. It's hard to do. Okay, now our flow rate is equivalent to what it was before. I'm going to set that point. And I'm going to save it. The cost to pump water at this new condition, we've got the same flow rate as previously, is $18.65. So we see a significant savings between using the throttling valve and using the variable frequency drive to slow down the pump. I'm going to do that again for this last condition. Okay, now we've got the equivalent flow rate. I'm going to set that point, and the cost to pump water at this point is only $22.62 versus the full speed pump at $38. We're still putting out the same exact flow rate and downstream pressure, but it's being controlled by the VFD, and that's saving money. Now that we've established our load profile utilizing the variable frequency drive versus a throttling valve, we can determine by the total water we're pumping for the year and the savings with the VFD whether or not a VFD installation is warranted. We need to know two things. First, on the bottom right corner over here, we need to know the total acre feet we're going to pump using this system for the year. So I'm going to estimate, on this example, we're using 400 acre feet. Plug that number in. And then, on our load profile, we got to come over here and give you the percentage of water pumped. I'm going to plug in three different numbers there. Let's say 50% of the time we're at full speed. There is no advantage to the VFD. This speed number 2, the flow rate of 91 gallons per minute, let's say we're at 30% of the time. And finally, to add up to 100, we would have 20% of the water is being pumped at that last speed. Based on this load profile scenario here then, of 50%, 30%, and 20%, at these different flow rates and different costs per acre foot, and pumping a total of 400 acre feet per year, we would save $2,220 on our power bill. If we use the VFD to keep the pressure level at 70 feet all the time, versus using a throttling valve to slow the flow rate down for the different size blocks we're irrigating. You could have different size irrigation blocks, you could have different size elevations. The variable frequency drive could be used to maintain the proper flow and pressure no matter what the different scenarios are. They can be set up to automatically do this. So this is the advantage of this. Now the load profile, if you change these numbers, the percentage of the water you're pumping could become less attractive. For example, let's say 80% of the time we're full speed, 10% were the second speed, and 10% were the third speed. Now our savings for the year is only $964. Now, a VFD cost is pretty expensive. And it's likely with this kind of scenario, it wouldn't be worthwhile putting a VFD in. So it just depends on the load profile and what percentage of your water you're pumping at these different levels. That's how you determine whether or not a variable frequency drive would be warranted in this case.
The decision of whether or not to install a VFD is not a simple one, and in all cases, a pumping expert should be consulted. However, the key is identifying the load profile. In the example that Bill just demonstrated, we had 3 different operating conditions, and we showed you the cost of each using a throttling valve with a motor running at full speed and with a variable frequency drive slowing that motor down. A key aspect of that load profile is the percentage of water pumped at each one of those conditions. In our first operating condition, a lot of water was pumped at the slower motor speeds, and the VFD saved us over $2,200. This might be enough to justify the installation. In our second example, though, 80% of the water was being pumped at full speed, and we saw under $1,000 of savings. This may not be enough to put the VFD in place. So again, identifying the load profile is key.